Guys, so happy Wednesday. One thing, I apologize, I've been a little bit late getting my videos up, and that's just because it's taking me forever to upload them to YouTube. But I'm looking into some changes for that and the way the format I record my videos in. And so anyways, I'll try to start getting those on time. So hopefully the homework's going well today. It's due at 5 o'clock today. Please shoot me an email if you have some questions. I can help you out and get you through the homework. Okay, so today we're going to start into line integrals. And these things are not too bad, but at first sight they can be kind of tricky. So let me just talk about what we've already done. We've done double integrals, and those are volume underneath a surface. Okay, so double integrals somehow give us volume. If we integrate the surface, it's the volume above the region we're integrating below the surface. We did triple integrals. Well, what are those? Well, we can't visualize a graph. You could call it hypervolume, but a better way to think about it is in terms of thinking of the function, the integrand being density, and then when we do the triple integral of it, it's like summing up somehow all of the mass, and so you get total mass. Okay, line integrals. So first off, what's the setup? And this part's going to be kind of the setup. There's actually two types of line integrals. I'm going to do what's called the scalar line integral today, and then probably a scalar line integral tomorrow or Friday, and then on Monday we'll get into the vector line integrals. But so the setup for a line integral is I have some type of curve, okay? Some type of curve here in the xy plane, all right? And then over here, I've also got a function like so. So here's z equals f of xy. It's some function, so remember I plug in x and y down here. And now what a line integral is if I take and I draw this curve like so, oops, down here. So here's my curve, C, and I take and I look at what happens to my function values up above this curve. So maybe there's the curve, and then what happens is as I plug in all these points along this curve, this traces out some type of curve up here, okay? So there, not too bad of a drawing. The line integral here, or what we call the scalar line integral, is if I look at this sheet below here, so it is just the surface that's below this surface that F carves out and above this curve. And I like to think of it as like this sheet right here, okay? So something like that. Take a look at that, looks pretty good. The scalar line integral is what we're going to call, it's the line integral over the curve of the function f of xy, and then this ds, the s is what we call with respect to arc length. It is the area of the sheet, is what I call it, above the curve C and below the surface that f graphs out. Okay, so that's what it is. All right. Now, how do we calculate this area? Well, normally I would sit and derive this, and usually what you do to derive it is you break this little curve up into small little pieces, but I'm just going to, given the situation, I'm just going to give you the formulas. And so the first thing you have to do is you have to parameterize this curve. And it actually has to be a smooth parameterization of this curve. So in other words, it's got to be differentiable. And if I parameterize this curve, say from t from A to B, so in other words, as I plug in t into these things, I get out the points along this curve. All right, then the formula for this scalar line integral, or in other words, the area underneath the sheet, is equal to, and give yourself some room here if you're taking notes at home, it's equal to, I plug in my functions of t, okay? And now, so what this is right here is, now I'm looking at just f acting above the curve. But now I need this area business, and this curve actually has some distortion, so that distortion is gotten by this arc length element. Okay, and this is the formula for a scalar line integral. So what do? We want to know the area of this thing. We plug in, we first off parameterize our curve, we plug those into our function, we integrate that, but the deal is this curve, depending on the parameterization, how fast we go or whatever, it's got curvature, this takes into account, and this gives me that area. All right, so let's do an example here. Okay. And now I want to talk about one of the things that's tough about these problems is you guys are going to have to parameterize your curves. Okay, so we'll say, okay, well, it's just this circle. Well, you have to parameterize it, so you need to know some kind of natural ways to do that. All right, so here's our picture. Let me see if I can draw this one. What does this function look like? X squared y. Well, it's kind of like a little sheet that goes up here. Okay. And I don't know if that does anything for you, but let's draw it a little bit more pronounced. And so what we're doing here is we are integrating this thing over a circle. Okay, the upper half circle. So I'm just drawing the in the first plane. Maybe I should have even made this just a quarter of a circle so you can see the picture. But the idea here is now that this thing traces out something along this surface, and it would be just this kind of rounded cup underneath there. That's about as good as I can get. It's not a great picture, but it's decent. Okay. So, how do we do this? First off, you've got to parameterize. So we've got to parameterize this circle. And there's actually a couple ways to do that. And I'll maybe do this, if we have time, I'll do this a different way. But here's one way to do it. The natural way in my mind is cosine of t and sine of t. And now here, we're just doing half of the circle, so my t is going to range from 0 to pi. Okay? All right, so not too bad. So now, let's see if I can fit this integral in the remaining room on the board. If I have to erase some stuff, that's okay too. All right, so one more thing I need before is I need the derivatives. The formula for this scalar line integral, I need the derivatives. So I need negative sine t, that's x prime, and y prime is cosine t. All right, so now we're good to go. So here's my function. Like I said, it's this like kind of, it's actually like a kind of a saddle, like a hyperboloid, I think is what we call it. That's what this is. We're integrating it. We're doing the scalar line integral over this half of a circle, and this ds represents the arc length element, is what we call that. So this is the integral from 0 to pi. That's the limits on here. You had to figure this whole part out, by the way. Okay, you have to come up with this parameterization. We'll talk about some basic parameterizations a little bit later. So I need to plug in what x is. It's cosine. So I get a cosine squared. I need to plug in what y is. It's sine. And then I've got this whole square root business. And I need to plug in x prime, negative sine, and I square that. So I just get sine squared. I need to plug in y prime. It's cosine. Square that. I get cosine squared, and then I have a dt. Okay, this represents the ds part. Okay, this is like the ds, and then this is the function over t. Well, as you can imagine, these are in general hard to compute because it's got a square root in it. Square roots and integrals don't play well with each other. However, in this case, when we're doing over circles and things, it's nice, and this just becomes 1. And so I just get this integral, 0 to pi cosine t sine t dt. Fine. And you can do this pretty easily with a u sub. So u equals cosine. Du is negative sine t dt. So remember, this is just a u sub. This doesn't have anything to do. This is just to evaluate the integral. Oh, sorry, there. Okay. And then when t is 0, u is 1. And when t is pi, u is negative 1. And so the moral of the story is this becomes a negative, which I'm just going to write as a positive and switch the limits of integration, u squared d. Okay, you can figure this out at home. I skipped a step there, but this is a step from back in Calc 1 that you all can do. And now that is u cubed over 3, evaluate negative 1 and 1, that's 2/3. And so there we have it. There is our first line integral. Okay? All right, so let me talk a little bit more about the parameterization. So first thing is, another parameterization of this one is you could actually just solve for y in that equation and let t be the independent variable. And this works, and actually you can plug it into all this, and you may think, well, I get square roots upon square roots. Well, actually everything kind of works out nicely, and it cancels. This works out pretty well. And it doesn't matter the parameterization you use. It turns out that's not a big deal. So usually when you have circles and things, you do the sine and cosine just because it works out pretty nicely. All right, so let's talk a little bit about a different format for this. Yeah, so I should say that it's independent of the parameterization. And so another format of this is if we let, this is maybe what we call a vector form, if we let this be the vector parameterization of our curve, here's C, then our line integral, we can write it in a little bit more concise way. It's the integral from A to B. I'm going to plug in R, treat it as a vector there, into F, and then what I do is I multiply by the magnitude of R prime. And if you think about it, this is exactly what that square root of x prime squared plus y prime squared was. It's exactly that. So this is a little bit more concise form. So a couple facts about this. About scalar line integrals. Okay. One is they do not depend on the parameterization of C. Okay. And in other words, no matter which way I go, whatever parameterization I pick, no matter which way I go, I'm going to get out the same answer. Now, there's one little caveat to this. If I pick a parameterization that like transverses this curve several times, like it goes back and forth, you won't necessarily get out the same answer, okay? But as long as it just travels the path C once, so it can start here, go here, or it can start at this point and go back, you're going to get the same answer no matter what parameterization you use. So think about the last example. I used this cosine and sine parameterization. I could have also used a square root parameterization to describe that. Okay. And the second is if C is made of several pieces, okay, so say my C looks something like this. So say I have a C, and usually these C's have to be smooth curves, but this is not a smooth curve, okay? But here's the overall C. Well, what I can do is I can break this into maybe 4 pieces, okay? And then to do the scalar line integral, all you do, and I'm just going to shorthand this, is you sum up the scalar line integral over each piece. All right, so let's do one like that, and then we'll call it a day. All right. Okay, so here we go. Here is an example of a curve that's split into several pieces, okay? It's the triangle, and by triangle, I don't mean the solid triangle, I just mean the perimeter of the triangle. But anyway, here's C. What did I do? Sorry, guys, the one I worked out earlier in my notes, this is a 1, 1. Okay, so here's C. And this makes a little bit better picture, actually. This is one that we can actually draw, see what's going on. So here is, and so I would say C kind of splits up into 3 pieces. Okay. All right, so in terms of what are we doing with this thing, well, this we can actually draw. So our function, f of x, y equals x, is just a plane coming out like that. Okay. And then what's going on here is I've got my triangle down here. And so what happens is this actually makes a little sheet like so, and then goes on the back end. And so I'm actually summing up basically these sheets down here. Okay, and there's 3 of them. So first off, let's just take this moment. How do we parameterize a line segment? Because we're going to need to do that here. We've actually got 3 of them. And so how we do that, say we've got point here, there's P and Q. Well, what your parameterization is you're going to do R, T. There's several ways to do this, by the way. You can figure out the equation of the line between these two. If you know the X and Y values of P and Q, you can figure out their equation. And then you can just do that. But this is a really easy way. And I'll tell you how I think about it. So make a vector out of P, and make a vector out of Q. And then you put T in there, and you let T go from 0 to 1. Okay? And the idea here is this is going to parameterize that little line segment. It starts here at P and ends at Q. Why? When T is 0, I get out P and Q disappears. When T is 1, the 1 minus T, I view this kind of like a light switch, right? Makes the P disappear, and I get out Q. And so it lights up at Q, and then in between, for T in between 0 and 1, it moves in a linear fashion from one point to the next. Okay, so this is an important thing that we're going to do later. So let's do this now. Back to the problem. Let me erase this for a second. We've got 3 pieces here. So I'm back over here. And we need to do 3 different line angles. So let's call this C1, C2, and C3. Okay, so for C1, we can parameterize it by the function. My starting point says the origin, 0, 0. And my ending point is the point 1, 1. So I would do this as 1 minus T, 0, 0, plus T, 1, 1. And then that is just function T at T between 0 and 1. And so my integral over C1 of x ds, what is this equal to? Well, it's equal to, I plug in this function, t, and here I just have an x, so I plug in t, and then I take the derivative of this guy. Notice r prime of t is 1, 1, and I plug that in here, and so I get square root of 1 squared dt, and I get a square root of 2 integral from 0 to 1 t dt. That's a half, so it's square root 2 over 2. Okay, so that's the first part of this. Let's actually make a little note of that here. Square root 2 over 2. All right, so now, just for lack of space, I'm going to erase this and do the next one. Okay. So now for C2. So C2, you can start either way, and actually I'm going to start down here and go up. This orientation is going to be important when we get into vector line integrals later, but for now, I'm going to start there and go up. So I'm C2, I'm going to parameterize it. It starts at the point 1, 0 and goes up to 1, 1. So I do 1 minus T, 1, 0, plus T, 1, 1. And when you combine everything there, what you get, and of course this makes sense, you get 1 minus T plus t, that's 1, and then I get t. And t ranges from 0 to 1. When you work enough of these, you get actually good at this, and you just realize, well, here I'm going to let x equal 1, and then y will go from 0 to 1, which is basically what we did here. Okay, so now the line integral of this part, x ds, is I plug in my parameter interval, 0 to 1. I plug in x equals 1. And then I plug in r prime in magnitude. And r prime is derivative 1 is 0, derivative of t is 1. And so this is just square root of 0 squared plus 1 squared. It's just 1. And anyway, here for this piece, I get 1. So this piece is 1. Okay, last one. And then we'll call it a day. So now C3, I'm going to go here. Let's just see if we can think about this to come up with the parameterization. So y is fixed at 0, and then x ranges from 0 to 1. So our parameterization here, and you can use the method I showed you earlier, but x we're going to let be t, y we're going to let be 0, and then t is going to range from 0 to 1. Pretty simple, right? And if you think about when I plug in t equals 0, I start here, plug in t equals 1, I end up there. R prime is 1, 0. All right, and so this one doesn't take much either. So finally, C3, x ds. I'm going to plug in t for x. I'm going to integrate from 0 to 1. And then my r prime, this is just square root of 1. I'll write it there just for the heck of it. This is going to be just the integral from 0 to 1 t dt, which is t squared over 2. When I plug in 1 and 0, I get a half. Okay, so this is a half. And there we have it. That's going to be the final answer. Is we're looking for this piece. And what it's going to be is I just add these three things up. Together I have 2 square roots of 2 plus 1 half. Oh shoot, what do we do with that? That's, let's see, that's 3 halves. I guess you'd write it like this. Yeah. That's it. All right, guys. So we'll continue with this. Again, I don't have office hours today, but please email me if you have questions on the homework, and I will see you all tomorrow for office hours, and I'll have another video for Friday. Take care.